Hello everyone and welcome back to Nunley Math. I'm Aaron Nunley and we are talking today about solving two-step equations. We are well into our unit on algebra for the pre-algebra student, where we are taking patterns and principles that emerged in elementary school mathematics, and we are using those to work with algebraic problems. That is, problems that have unknown values represented by variables. So far in our video series, we've talked about several mathematical properties. The definition of subtraction, which we define as the same as adding the opposite. Subtraction is the same as adding the opposite. We talked about the commutative property that says when we have a string of addition or a string of multiplication, it doesn't matter what order we write numbers in. We talked about the associative property that says if you have a long string of addition or a long string of multiplication, it doesn't matter how you group the numbers. We talked about the distributive property that says if I have this many of a group, I have this many of everything in the group. And then in our last video, we talked about the property of equality that says I can do whatever I want in an equation as long as I do it on both sides. And we connected that with the identity property that says adding 0 and multiplying by 1 do not do anything. At this point, you should be at least relatively comfortable with those properties, even if you're still struggling to know the names. If you are comfortable with those, you're going to find today's lesson to be very easy because we are simply doing things we've done in the previous lesson, but we're just combining those to solve larger and larger problems. The last lesson we did on solving single variable equations, I gave you problems that looked like this. We said single step equations can be solved by trying to get the unknown value by itself using the property of equality. And we said that when we use the property of equality, we want to try and pick things that are going to make this number go away. This plus 4 we want to go away. And so we intentionally pick a negative or minus 4 because minus 4 and plus 4 together give us a 0. We said those were additive inverses or opposites. And we said we wanted this to be a plus 0 because when we use the identity property, which says anything added to 0 stays the same or does not change, we get the x by itself and we find out that x has a value of 3. This is actually one of the examples. I think it's the first example we did in that lesson. I put it up here just to remind you of this pattern: equality, computation, identity, and to remind you that this is the basic principle we use when solving algebraic equations. We can also check that by rewriting the original problem, plugging in the value we said would work, and then simplifying the sides to see whether the two sides will match. And if they do, we know we have the right answer. This is very, very important and very foundational for what we're going to do today, because this equality, computation, identity pattern is going to be used repeatedly to solve increasingly more difficult problems. So if you're confident and comfortable with what you've seen here, then you're going to want to continue watching this video. If this is a struggle for you, you really need to stop watching this video and go back and watch the solving single step equations video. If you're continuing, I'm going to assume that you're ready to rock and roll with this, and I'm going to keep right on rolling. Notice, in this equation, I no longer have x with one thing done to it. You'll remember on the previous example, I had an x, and the only thing that was done to x was adding 4. In this example right here, I've done two things to x. I've multiplied by the 5, and I've subtracted the 13. I've done both of those things. So if I want to know what value x has, I need to get rid of the minus 13 and I need to get rid of the times 5. You'll remember the property of equality says I can do anything I want as long as I do it on both sides. Or whatever I do to one side, I have to do to the other. So I have a lot of options available to me. Now, we said that when we're going to use the property of equality, our goal is always to try and get this minus 13, remember, we want to get this thing right here to become a 0. What can I do to a minus 13 to get it to turn into a 0? Well, if you remember, the additive inverse of a negative 13 is plus 13. Because a negative 13 and a positive 13 when added together give us that plus 0. And we said the identity property says adding 0 doesn't do anything. Notice where we're at now is much simpler than where we were at a few moments ago. We use the equality computation identity pattern to try and get things to go away. Notice I still have this times 5 here. If I want to get rid of a times 5, I need to use something we learned yesterday or in our previous video, and that is to get rid of something that is multiplied, you either have to divide both sides by that number, or we did say you could multiply by the multiplicative inverse. In other words, I know that to get rid of a times 5, I divide by 5 because these two things divide out and become a 1. And the other side becomes an 8. If I had chosen instead of division to use multiplication, I could have multiplied both sides by 1/5. I'll do that over here. 1/5. 1/5 times 5 is 1x. 40 times 1/5 is 8. So you can do it either way. Either multiply by the reciprocal or divide. Remember, division's definition is multiplying by the reciprocal. Either way, we get this to be a times 1. We deliberately picked the multiplicative inverse, or that times 1/5, or the inverse operation of division. We intentionally did this because we wanted this to be a 1. Because as soon as that's a 1, we know the multiplicative identity says multiplying by 1 doesn't do anything, and we're finished. Now, I did that pretty quickly because we've already done this exact same process yesterday. Notice, equality, computation, identity, equality, computation, identity. I do this pattern now twice in a row. Yesterday, with a single-step equation, I just did it once. With a two-step equation, I just do it twice. As always, we can check this by rewriting the original problem, substituting in the number we said should work, and then simplifying. 5 times 8 is 40. 40 minus 13 is 27. When the sides match and what shows up is true, I know I have the right answer. If whatever you plug in did not work, then you would need to go back and work the problem out again because you've done something wrong. This pattern, equality, computation, identity, is going to happen over and over throughout the rest of the unit. So you want to make sure you're very comfortable with that. I have a second example over here. I would recommend pausing the video and trying this one on your own. I'm going to assume that if you wanted to do that, you already have, and I'm going to keep right on going. My goal is to get this x by itself. I've done two things. I've multiplied by a -3, and I've added a 14. How do I undo that? Well, I'm going to use the property of equality to subtract 14 from both sides. I picked minus 14 because I know these are additive inverses, meaning when I add them up, we're going to get a 0. And I want that plus 0 because the identity property tells me that I don't need to write it down. Plus 0 goes away. It doesn't do anything. How do I get rid of a times -3? You have two options. Option number 1, you could multiply by the multiplicative inverse. That's the times -1/3. Some of you may prefer to do it that way, and that's okay. -1/3 times -3 is 1x. -36 times -1/3 is 12. If you want to do it that way, that's fine. Your other option is to use the property of equality to divide both sides by -3. Dividing by -3 and multiplying by the reciprocal are the same because -3 divided by -3 gives you 1x. -36 divided by -12, or -3, is 12. I wanted this 1 because the identity property says multiplying by 1 doesn't do anything, and so I can get rid of it. If I wanted to, I could also go through and check. Remember, rewrite, substitute, simplify. If what's left is true, you know your answer is correct. Whew. It's a lot, right? Notice again, equality, computation, identity, equality, computation, identity. Occasionally I'll get a student who says, Mr. Nunley, can I get rid of the 3 first? And that's a great question. The property of equality says I can do whatever I want as long as I do it on both sides. But just because I can do anything doesn't mean that doing anything is helpful. For example, we specifically picked things that would give us a 0. I could have subtracted 18 or added 47 or divided by 36, and it would have worked out just the same. It's just I want to pick things that are easy for me to use. The problem with getting rid of the times -3 first is if I'm going to divide both sides by -3. You're right, this does become 1x, but I also have to do 14 divided by -3, which is -4 2/3 equals, this is -7 1/3. So by dividing by the -3 first, I ended up creating fractions that are harder to work with. Could I still solve it this way? Absolutely. But I think you're going to find that if you get rid of the addition and subtraction first, and then get rid of the multiplication second, I think you'll find this is going to work out a whole lot nicer for you. Let me erase all of this. That's not bad, right? Tell you what, here's another one. Notice that I have put the 42 on the other side, the -42 on the other side. This does not change anything. It just makes it look a little more complicated. I'm going to recommend that you pause the video, try it on your own, and then watch me do it. I'm going to assume if you wanted to do that, you already have. I'm going to use the property of equality to get rid of the -35. And when I compute, notice I got a 0. I intentionally picked additive inverses to get the 0 because the identity property says that I don't need that plus 0 anymore. How do I get rid of a times -11? I can either multiply both sides by -1/11 because those are multiplicative inverses and will give me a 1. Or, if you would rather, and most people prefer, I could divide both sides by -11. -77 divided by -11 gives you 7. -11 divided by -11 gives you the 1. That was the goal. I intentionally multiplied by the reciprocal or divided by whatever would give me a 1 because the identity property says we don't need that times 1. And you have your answer. Now, it makes me uncomfortable to say 7 equals x. I would usually write that as x equals 7. It doesn't matter which side of the equal sign things are on. If two things are equal, they are the same regardless of the position. We call that the symmetric property. The symmetric property. It doesn't matter what side of the equal sign you put things on. If they're equal, then they're equal. And then, of course, out of obligation and making sure I didn't shortchange you, I did go ahead and rewrite, substitute, simplify as well. One more? Let's do one more. Again, I've got the equals 47 on the other side. It does not change anything. We're going to do this the exact same way. You have to be careful on this one. This minus sign really tends to throw people off when they're trying to work these out because they say, oh, to get rid of a -13, I need to add a 13. The problem is this minus sign is not with the 13. This 13 is positive. So be conscientious about that. That will really throw you off. My personal recommendation to you is that you use the definition of subtraction that we learned in our previous videos and just change that to plus negative. Because if you change it to plus negative, you're much less likely for that negative sign to confuse you. Notice it's kind of close in here. I probably should put an extra space in there. Just be aware that it's very common to lose track of negative signs, and so you're going to want to be really careful about that. How do I get rid of a plus or positive 13? Definition of subtraction is what I use to change that. Here's another one. Go ahead and give this one a try. Notice again that equals 47 is on the other side. It really does not change things, although it does make things a little bit confusing. Also notice that I've got a minus sign in here. This minus sign in particular, because it's in front of the fraction and in front of the x, is problematic for me. So I'm just going to go ahead and use my definition of subtraction to get rid of that. I think you're going to find the larger and more complex the problems get, getting rid of subtraction is going to be very, very useful for you. So just change it to adding the opposite. And I'm going to do something else here. I'm going to go ahead and move that equals 47 to the other side. Remember, if two things are equal to one another, it doesn't matter which side of the equal sign you put them on. So for me, it's just more comfortable to have the equals 47 on the right. I use the symmetric property we just talked about. Here's what I'm going to throw in for you. I don't like the fact that this is 13 plus negative 2/7 x. I could solve it this way, but to me, it makes more sense if the plus 13 is on the other side. Do you remember what rule says I can switch the order on my addition? That's the commutative property. Commutative property says if two things are added, it doesn't matter which one comes first. Now this feels a whole lot better to me. Could I have solved it straight from this original one? Absolutely. But this just makes more sense to me because I've seen it more often. How do I get rid of a plus 13? I use the additive inverse to get my 0, because I know from the identity property that plus 0 doesn't do anything. How do I get rid of times negative 2/7? To get rid of multiplication, I want to multiply by the reciprocal or the multiplicative inverse. That's negative 7/2. Notice this side becomes 14/14, which is 1x. 34 times negative 7 is going to be, let's see, 34 times 7 is 210, so 238 over 2. What is 238 divided by 2? You might have to work that out by hand, but it comes out as negative 119. Please don't feel as though you have to do this in your head. If I weren't doing this in the video and didn't have it worked out ahead of time, I would have probably gone off to the side and actually just set that up as a fraction and done, okay, let's see, that's a negative 7 over 2. I would have gone through all those good fraction steps that we would ordinarily do. Notice now it's 17 times negative 7, which is that negative 119. Just because I'm not showing the computation here on the video, please don't feel as though you should be ashamed for doing that. If I were doing this, I would work that out using my fraction rules. I just don't include it here for the sake of speed. Lastly, I can get rid of that times 1 using my identity property. Notice again, you have your equality, which apparently did not appear here, my equality, computation identity, and I have equality, computation identity again. At the beginning of the problem, we tend to do some odds and ends on occasion to rearrange things so way they're more comfortable, but most of the time you're going to end up repeating that equality, computation identity a couple times. You'll also notice that for the sake of time, I am not going to do the check for this one, but you could do it just as well. Rewrite, substitute, simplify, and see if they match. Now that's a lot to absorb. I've thrown it all at you very, very quickly, but hopefully it was slow enough to make sense, especially if you understood the previous video on single-step equations. We're just kind of stretching that and expanding it just a little bit. That's really all I have for you today. I hope that made sense for you. I do wish you all the very, very best of luck. Take your time with this. Be careful. Keep an eye on those negative signs. You're going to do great, right? Wish you all the very, very best. Bye-bye.